Hello everyone, welcome to episode 3 of Warsaw.ai. Thanks for coming. Today the event is sponsored by ByteDance, so also during the after party you can meet and talk to engineers, researchers from ByteDance. We are happy that they are supporting us. So we'll start with a talk of a representative of ByteDance, Mariusz Moczala. Later, Piotr Migdał will give a talk, and finally, Tomasz Trzciński, our host today from Warsaw University of Technology. After three lectures, we'll have after party as usually. So the networking part, opportunity for you to network. Let's start. So without further ado, I will give a voice to Mariusz from ByteDance.
Thank you. Hello and welcome. My name is Mariusz Moczala. I'm working at ByteDance as a software engineer. And today I will talk about performance optimizations of the convolutional neural networks. But before that, let me introduce you a little bit to what we do at ByteDance. So the vision is to create to build platforms, global platforms for content sharing and interaction. And as a company, we has been founded 7 years ago. Right now we have over 30,000 employees, so the growth is extremely fast. Our products are available across the world in over 150 countries. And in over 28 countries we have already our offices. And R&D actually is located in China, in Silicon Valley, and right now also here in Poland, in Warsaw. One of the platforms we have is TikTok. This is the one of the most often downloaded application on iOS and on Google Store. And probably you already heard about this application. It is more and more popular in Poland right now, mostly in between teenagers for like dancing and lip syncing. However, in United States, United Kingdom, India, Japan, we already succeed to diversify these videos in different domains. And even our CEO thought that the TikTok is actually a window for many people to the world, yeah? And actually you can use it in travel for promoting cities and so on. So what the TikTok is, it's a simple application where you can record short videos, like 15 seconds wide. And on this video, you can apply some filters, yeah, where we use deep learning to empower it. And here's an example. Let's look at this short video. So this is actually recorded on TikTok, applying different filters to affect the hairs. And if you look carefully at illumination, at shadows, and so on, everything is recorded in real time. Yeah. So I will right now talk how to optimize it. And actually, with this video, I found that this filter not only works on beauties. So I tried to apply this filter on myself, but unfortunately, it failed to locate some hairs. Yeah. So, okay, let's move on. Okay, so to make filters like this one, we need to apply some like deep learning. Probably you would use convolutional neural networks. And in this convolutional neural networks, the mostly computationally heavy layer obviously is a convolution, yeah? So it usually takes like 80% of total execution time or even more, yeah? So anything we improve this convolution, this will dramatically affect the whole application, yeah? So I will, at the very beginning, I would like to tell you that optimization is not only the theory, but mostly out-of-the-box thinking, and you will see through the slides how it looks like, yeah? So, but even before, if some of you still don't know what is the convolution, I will just briefly remind. Yeah, so like when you have a input image, okay, and some filter, also named kernel, you can use it to produce an output. Okay, we use this symbol in mathematics for convolution. And the output is created that we apply the filter. Each value in this filter is pixel by pixel multiplied with corresponding pixels in input image. And then we add up these values, and like here, we produce it only one output. And we apply this filter on every possible location on the image. Yeah, so we produce output looking like this. And now, so if you look at this algorithm, it's quite complex to compute it. Actually, you need to perform as many operations as you have pixels on the input image multiplied by size of the kernel. Yeah. So the very first thing we can optimize here is the memory layout, because if you look here, we are on a two-dimensional space, or even we have third dimension as a depth, like channels in RGB in image. And the very first thing is to optimize is to better aligned in the memories, so the cache in the CPU will be used properly. Yeah, and the example here is image to column matrix algorithm, which performs a transition from the image representation like here to the representation like here. So we put all the pixels in the column manner, and the kernel here also we put exactly in the format like it is stored in the memory, pixel by pixel. And the advantage here is that we can actually compute convolution using simple matrix multiplication. Okay, and for matrix multiplication, algorithms are already perfectly optimized, yes, because all the data is properly located in the memory. So, but another advantage here is that usually we have multiple filters, yeah? So we don't need to perform many matrix multiplication. We can do this at once. We simply add more and more filters here, and the output we produce is exactly in the format we expect. Yeah, so as the output image. If we even though we can apply a mini batch by adding more columns from other images, and if you perform some interleave here, it will also be produced in the right format. Yeah. So after this operation, you don't need to perform any post-processing. Yet another approach in optimization is Vinograd. I like this algorithm very much. It has a very complex mathematics behind this, but in practice it's very simple, and I will explain it to you how to use it properly, because programmers usually fail at certain point implementing this algorithm. So if you look here at the formula, we have this little b, which is this matrix, a fragment of the input image, and G is a kernel, and this red rectangle is Y, yeah, is the output. So all of these are matrices used in this formula, and those matrices are provided by the document, the Vinograd algorithm, and all of them are constant. They don't change, yeah, during the execution. And here, like, because G is also constant during the execution, at least for inference, yeah. So, and we have G here. So all this operation we can execute at once at the very initialization of the neural network, and then we can reuse it for computation. And for this guy here, actually, if we look closer, so yes, exactly this is written here that we need to perform matrix multiplication, yeah? But if we look at the B matrix and A also, we will find that it is actually constructed of zeros, ones, and minus ones. What does it mean? Anytime when you have a zero, so multiplying by zero produces zero. So why actually do we perform this operation? Also, if we multiply something by 1 or minus 1, So we can convert this operation here to simply addition or subtraction instead of executing quite complex multiplication. Yeah. So this is the power of this algorithm. Yet another approach, very similar, is to use a frequency domain. Here is another mathematical theorem which tells that if we convert the input image to the frequency domain using FFT and the filter, then we apply element-wise multiplication. So we will produce the result of convolution of this image by filter, but still in frequency domain. So after performing this inverse FFT, we got exactly the result for convolution. And what is important here, that no matter how big the filter is, the complexity of whole algorithm is constant. So even if you have 100 by 100 pixel filter, it will compute as fast as for 3 by 3. Yeah? And usually this algorithm is used in image processing, for example, for blurring images or something like this. And you can see it here. So what I stored here, on the very first row, you have frequency representation of the Gaussian filter. And in the second row, you have this Gaussian multiplied with image in the frequency domain representation. After performing inverse transform, you will receive this kind of result. Yeah? And if you apply like naive implementation of the convolution for this algorithm, it will probably take, the execution will take time like 1 minute, 2 minutes, 4 minutes, 8, and so on, yeah? Up to 32. But if you apply FFT, it will be constant. Not very good here, but it will be like 4, 4, 4, no matter how big the filter is, yeah? Okay, so basically, I explained to you how to optimize convolution, yeah? So there is many ways. So which algorithm is the best? Actually, it depends. It depends on the size of the filter. And for example, like we have 1 by 1 pixel convolution, so it's nothing more but dot product, yeah, because we go in depth. For 3 by 3, we can use Vinograd, which is the best for this case. Also for 4 by 4 filters, but we don't use it in convolutional neural networks. And the FFT comes from like 13 by 13 pixels to almost every case, yeah. And actually, like in this position, I use 2 algorithms because it depends on the processor we use. So sometimes one is better, and other time another. So we already discussed that we can align the memory to perfectly fit cache. We can also optimize math, but here we should also optimize the amount of the memory we use. So to reduce the memory as much as possible. And here, for example, when we perform convolution, max pooling, and ReLU, and the activation function, yeah, usually in neural network frameworks, we store the intermediate data in the intermediate buffers. But honestly, this max pooling is working on 4 pixels only, yeah? So why not to combine these 2 algorithms and even this one, because this is element-wise operation, and to avoid using this additional memory, yeah? Because accessing the memory costs the CPU the most of time, yeah? So we can improve it a lot by doing this kind of operation. Yet another approach is to use different data types. And here for the reference, I stored the representation of the floating point numbers. The most commonly we use single precision in neural networks, but once the hardware appeared supporting this half precision, we actually find out that neural networks still trains very well on this lower format, but execution on this takes much less time. Yeah? And for some networks, which doesn't expect a wide dynamic range for the real numbers, we find that actually we can use just integers for this. So we just use mantissa and sine, and that's it, yeah? And we can use integers instead of floating points. And yet another example is with this exponent 8-bit. It's still integer, but instead of mantissa, we use exponents, so sine and 2 to the power, raised to the power of exponent. And where it is used only in the networks where dynamic range is much wider, yeah? And we also tried networks on a 4-bit, but we don't have hardware to support it, so it's still exotic data type. And this 1-bit integer is very funny. I would like to tell a little bit more about it, because for inference, you can, we basically have a hardware for doing this, and it is a CPU, yeah? So any operation you can do using logical operation, like OR, AND, exclusive OR, and even convolution is very simple to compute here, because you simply apply pop count operation. Pop count is when you have a matrix filled with zeros and ones, so the pop count will be number of ones in this matrix, yeah? So the inference is very simple. But what about training? In training, we need to compute gradients. We cannot have a gradient in range like from 1 to 0 in integers, yeah? So we actually, for training, we use floating point numbers. However, these floating point numbers are used in a form of fuzzy logic. This means exactly that we apply a probability. So if we have a gradient in range between 0 and 1, then we will randomize the value either 0 or 1 according to the probability of the occurrence. Yeah? So for 0.75, yeah, you have 1/3 probability of achieving 0, and the rest for 1. Okay. So I told you already a few times that this is always the out-of-the-box thinking, the optimization. Yeah. So many people try to analyze what exactly is produced by the neural networks after the training. And here I have an example of different graphical representation of the weights of first layer trained on the images. Here we have AlexNet, GoogleNet, CIFAR, and VGG. And actually it looks very same. The models are completely different even from different years, yeah? But it still looks very similar. So if we analyze what exactly is produced here, so we can find out that we use certain frequencies, you see, like in the line here, some phase, also rotation, but I grouped these kernels here in one group, which is colorful, and some of them are white and black. Actually, this is not true. You should treat all of them as a pair of the colors, where one color is a color and another is its negation, and it always happens this way. Yeah, so like here you have black and white, pink and green, orange and blue, and so on. And to describe also, it is worth to say that all these filters are surrounded with bell-like shape, yeah? Distribution like Gaussian or something like this, yeah? And to describe this, we can apply Gaussian Gabor filters, yeah? And this Gabor filter actually uses here this bell-like shape with Gaussian and cosine wave, and that's all. So it will produce value in range of 0 and 1, and this -1 to 1, yeah? The lambda here we use to align it to the specific neural network. But why I am saying here? Because if we look again at the colors, so this is all the possible combinations of the color pairs that might occur in the neural network. And these colors, that we have 27 pairs, came from that we have RGB, free option, and 3 possible values to represent this: -1, 0, and 1, where 1 is a color and -1 is its negation. Yeah, so it gives us 27 possible pairs. But this in the middle, it's all set with 0. So neural networks cannot make any use of this filter, yeah? So it never appears in the neural network. And all of this color, like here and here, are complementary, yeah? Or here and here, here. So this means also that, yeah, because we have a color and negation. So this means that we are actually using only half of these pairs. So it is only 13 possible colors. So why am I saying about this? Because basically when you train a neural network, you can use a transfer learning to transfer data, pre-trained data from one network to another, just to speed up the process of the training. So for example, when you used one neural network to classify dog races, then you can reuse the network to classify cars, for example, yeah? And here, if you don't have, if you are, for example, a scientist and you prepared your own model, so you cannot apply transfer learning to speed up the training process, yeah? But you can, certainly you can apply these Gabor filters. And I have an example here. So when you have a CIFAR, for example, yeah, it produces the output like this. And if we apply these Gabor filters to the CIFAR, you can guess what? But the training will speed up by twice, okay? With this simple. So we initialize the very first layer with these Gabor filters, and all the other layers remain initialized with random values as usually. And you might be wondering how it is looking after the training process. So it is looking like this. What does it mean? It basically means that the neural networks actually very like this kind of filter for initialization, yeah? Because it didn't change too much. So as I told you, this is yet another approach to make optimization. And yeah, and here we actually didn't increase the performance of a single iteration, but rather the performance of whole process, because the accuracy, the expected accuracy, we can achieve in half of iteration. What is the most interesting here is also that it applies to all of the models with different speed up, yeah? But it's a little bit more tricky, but let's stay here. Okay, so just to finalize, recently I was working on this kind of stuff at ByteDance, and I really wanted to mention it. What does it is? So at ByteDance, I was asked to improve the performance of ASR training, and because we are using cuBLAS for all the computations, I found that it is quite hard because the NVIDIA is already providing well performing library. Yeah? So what can we do? Actually, I found that here at ByteDance and actually most other companies, we do all the computations on the GPU. Yeah? If we have server with 8 GPUs, something like this, yeah, we only use GPUs, and the CPU at the time is not used completely. So why not to use a CPU as a computing engine? Yeah? If we create a list of tasks, like here, if we put the task at the end of this line, it will certainly deliver the result in longer if we would use CPU for this computation. So I came up with the idea creating this scheduler that enables CPU as an additional computing engine. And what is the most important here, that this scheduler is also able to perform all the data transfers from CPU to device and back whenever needed. Everything happens in the background. And moreover, if you allow the scheduler that it can drop a little bit accuracy, it will try to apply this half floats instead of single precision, and everything happens in background. It computes the execution time, make estimates, and from the programmer point of view, you can see it as a single-threaded BLAS library on a CPU. So it is kind of heaven for scientists. Yeah. Okay. So basically, when you perform optimization, you should optimize your math, optimize memory layouts, reduce memory usage, and utilize your hardware as much as possible. So apply multi-threading to use all the cores, perform vectorization and fully utilize your GPUs. Yeah. So, and as always, remember to think out of the box. So, I hope I interested you a little bit at least. And this is the at least some of things we do at ByteDance. And we kindly invite you to join us. Yeah. And I would at the very end just add some note. If you are still not interested with this optimization, I can tell that in half hour of my work, I made an improvement that reduced the cost of using many servers by few $1 million, yeah, after half hour of work. So if you think if this is a good path for study or not, I'm leaving it up to you. So thank you very much.
So in general, like to give you an introduction, I'm this kind of person who switched from science to data science, and I'm very happy with that choice. And in general, what I do is I train people. So I explain complicated things in a simpler way. And in general, reality is complicated. It's more or less like that. If you do it in the standard way, so basically a typical lecture, a typical book, which goes step by step, one thing is super boring. Second thing, very often you miss all the things because almost everything happens in the interconnections. Though it's possible to go somewhere in between. So maybe you don't show the full reality, but at the same time, it's close enough and it's useful enough. So before doing data science, I did things like quantum computing and quantum information. And unless you have background in physics, you are as much lost as Frodo is. But the thing is that I was able to teach quantum mechanics to high school students. And it turns out it, takes a few weeks, but after that, no matter if it's in Poland or in Catalonia, they're able to grasp some key parts of quantum mechanics. So it's not about something being complicated. I don't think that there are that many things complicated, just it's not always easy to find a good approach in which step by step people can start learning things. And at some point even I decided to go one step further to create a game which is more like drag and drop. So you don't need to spend even a few days or a few weeks to be able to interact with quantum mechanics. And in some way it was basically computation with tensors before it was cool. So there are tensors in JavaScript, and this is interface, drag and drop, a game. Some people apparently like it. But let's go to AI or machine learning. So when it comes to presenting a lot of data in simple way, it's important for many things. One thing is to keep track of the papers and of state-of-the-art models. So it used to be that the main criterion for AI was ImageNet, networks, and we saw step by step how it went basically from something not too practical to being beyond human level. By the way, I totally recommend this site. It's a very new one, but with a long list of state-of-the-art models from various fields. So it's not only about vision or ImageNet, and very often with a direct link to its implementation. So it's not only you can know that there is a solution, but you can use it as well. And when it comes to visualization, sometimes also it's crucial to show a complicated model, very complicated one, in a simpler way. So for example, this is from a paper by DeepMind, when they show various activation maps and decision strategies for AI. So it's not only for showing in a simple way things that are not too complicated, but also for more advanced stuff. Or when you want to inspect models. And again, there's a lot of research into looking inside models for various reasons, both when it comes to being sure what's going on, if you can fix that, if we can modify, is it looking at things that shouldn't matter at least in our opinion, or maybe it's illegal to base our decision on some parts of the image or other piece of data. And when it comes to such interactive things, like at some point even I started collecting things which interact in the sense that they're not only tools you can use for production, but also you can interact with it more or less in a plug-and-play way. There's a list. If you want to add something, well, it's open source and open for contribution. But let's go to something more low level. There will be a small quiz, or a small question. What's that? So anyone? You should know. LSTM. Yes, LSTM. So there are questions for LSTM, and if you know what is vector calculus and stuff, it's very easy to read those equations. But it doesn't mean it's easy to know what's going on. For me, it was like, okay, some equations, what's going on? But then it's possible to show the same piece of data in a way which is more readable. When you have a diagram, we can look at it step by step, and then think, okay, it's a block. There's a piece for forgetting things. There's a piece for memorizing things, into what and where basically, and then for memory readout. Of course, it's much better with a walkthrough, step by step, but still for me, it was the first time when I understood what's going on in an LSTM network rather than a bunch of equations. And the same thing, like when you show things to other people, and if you don't want to explain in detail what's going on, this is actually from one of my blog posts, showing what is transfer learning. And basically, okay, you have some network, okay, you have it back. And then that, well, you have an image in the network, and if you do transfer learning, basically you cut its head, create a new one, and freeze weights, but with frozen weights of the previous one. And again, it takes a lot of cognitive load of describing what do you mean by changing head. Well, obviously, you need to have different outputs, for example, but it's not all. When it comes to, it's also very helpful in the training process. So I guess some of you may use TensorBoard or other tools for visualizing training process and keeping track of that. Here I will do a plug of shameless self-advertisement, because it's a library I started developing, which is basically for keeping track of the training process in a Jupyter Notebook. So mainly I use it for very small projects or for teaching, but still it's like, I don't know, has 600 stars or so on GitHub, and well, a lot of people wanting their stuff there. And the idea was just to make it basically plug and play with a few lines of code, and here we go. And the same thing when it comes to inspection. I think like when you train in blind, it's not enough just to look at log loss, accuracy, or whatever metrics we choose. It's also crucial to look at each detail of data. For example, like there are quick draws from Google, a simple convolutional neural network, and we see that, well, one is misclassified. It is a candle, but there's a prediction that it's a lighter. And again, do you have any guess why does it think that it's a lighter? You cannot deduce that, but maybe you have a guess based on this very, very small subset. So.
There are more lighters?
Well, maybe, but actually this data set was very balanced. But yes, it's a very common case that everything is the main class or the most prevalent class. But in this case, actually, I think it's because it's wide. Most candles were short and were very thin, and most lighters were much wider. So it thinks like, oh, maybe it's a lighter. And again, based on that, we can add some augmentation or change our data set or anything so that it does not produce such errors. And we can go even a step further, like looking at interactive confusion matrices, so not only knowing what are the common mistakes, but to see misclassified examples. Here I look at some network from CIFAR, and it was very easy to see that, or kind of easy, what are the patterns. For example, if everything is green and brown, very often it's thought it is a frog. Or in this case, there's a pattern here about birds misclassified as frogs. And I think it's about basically facial close-ups. A lot of dog pictures in that setting, so it guesses it's a dog. And again, solution data augmentation. This is like a beautiful solution for confusion matrices. Things like by Google, when you can look at examples, create confusion matrices, look at overconfidence of neural network, or when it's not too sure. But usually it's much simpler to make basically a matplotlib plot and see what's going on, and very often it's enough to look at the data. So, but as all new training models, it's also about models itself. And for example, if I give trainings in machine learning, sometimes there are people who just start their adventure into machine learning. For example, there are software engineers, and then it's very easy to show various algorithms first drawing them, ideally, again, in interactive way. So here's the decision tree, here's the matrix factorization, and you can also interact to see what's the optimal number of dimensions. Here is word2vec, and here's a thing like from random forest. Yes, it's from random forest, feature importance, or other stuff. And as basically as a side note, I think that when showing things to other people, this thing is so much better than just a NumPy array, because even though it carries the same information, more or less, as humans, we immediately see what's going on, which features are important. And when you just know it's like feature 5 is the most important one, maybe we don't know that, well, it's something which shouldn't be in our dataset in the first place. And when it comes to the same thing, when it comes to models, very often when I give trainings, one of the first things I show them is not a single magic black box. AI is not like some magic spell. It's a series of various algorithms. Some are very simple, some much more complicated, and each different algorithm performs different data set with various features. The similar thing goes for neural networks. So this is a similar idea, but for neural networks, a very small data set, and just one hidden layer. But at the same time, it's also possible to show that without this hidden layer, it would be possible to separate a circle from a ring, because basically we cannot cut it with a line. And based on this thing, I wanted to say, okay, maybe I can go a few steps better, a few steps further. And for example, try playing with that, with this kind of scikit-learn or TensorFlow playground plots, and create them matplotlib from neural networks. And it was kind of interesting, because sometimes we saw that even with the same network, just because of different initializations, we get a different result. Sometimes very similar, but sometimes, well, far off. And then one step further, so okay, maybe just make it interactive, be able to play with a classifier, or maybe other way. Play with a data set so that you create a classifier by hand. It's like it's from Karma, very nearby. Also, like this is nearby Pertinka, it's that way. And also actually tested it on kids in Bielsko-Biała, my hometown. And what's that? Well, basically a way in which we can draw a classifier. Here, it's like there's a very low contrast, so you won't see the main part. It's possible to reduce contrast a bit. There's like a reddish and greenish shade there, unless you see it very well. Okay, you see, the different screen works very well. And with the same plot, we can show various measures of accuracy, so like performance from the accuracy, but also other ones like precision, recall, and basically here all confusion matrix derived metrics. And here we see like if it goes. So this report, like this is a project with Kasia Kańska from eMove, and we developed that as a didactic tool / a game. So one thing we can do is we can look at data set, we can draw things, graphic classifier, see how does it go, and see, okay, precision high or high-ish, recall high. We can look at various metrics, including the full confusion matrix. And by the way, even F1 score can be visualized that way. But I think that what's more interesting is just to look at it as a game. So we have a few levels. Let's say all to know. And how should I split those data points? So just say you do it that way, my way. So let's say do that way. Is it good or not? Pretty good. Okay. So it's pretty good. Like I see like accuracy 93%. I think it's fine. Precision 92. Recall 92. And then I click validate. So I have a different data set from the same distribution, but now I see, well, it's way worse. See, so like all metrics are way worse. Because what I did, well, I did some kind of overfitting where basically I fitted my classifier, my data set, but not to the pattern, not to its distribution. And basically in this case, step by step, there are levels more and more complicated with data. And just to visualize what is it that we need to have a prediction for each single piece of space, but at the same time, we want to make sure that we don't overcomplicate things. So it's not just a memorization, but some underlying pattern. And at the same time to show that very often it's not possible to create a perfect classifier because there's a lot of noise, and no matter what you do, there is noise and uncertainty, which maybe is less profound in this case than, for example, when you think about convicting criminals or doing heart transplants, etc., etc. And one last part, not from this game part, but this playground, is that except from various drawing tools, I want to compare it to algorithms. So just you have nearest neighbors, and you can show that, okay, you did it that way, and how would nearest neighbor do? Or radar-based function, SVM, or Gaussian processes, or decision trees, etc., etc., or naive bias. And basically, it's a project that is going on, so just thinking how to approach that, what to use, which algorithms to compare, if to dive deeper into also predicting probabilities rather than just binary values. Here, by the way, it's like, I don't know, it's like which colors are the best, because it's also matter of both perception and one's own preferences. So here's a very much open-ended project. But if you want to either contribute to that, test that, play with that, contribute to that, or just use various widgets for precision, accuracy and stuff for didactic materials for students, then just feel free to do so, or feel free to contact me. Where's the presentation? Okay. And if you want to, especially invite you for a visualizing machine learning co-working / hackathon, which takes place at the same Technical University of Warsaw this Sunday. It's like a very laid back, so you can commit at any time, leave at any time. You can join other projects. You can work on one of your own projects. So thank you.
Okay. Thank you, Piotr.
We're turning videos into comics. And what exactly that means is you take a video out of YouTube, Vimeo, TikTok, out of famous ByteDance, Twitter, or your own video or images. You upload it to our platform, or you can also do the magic and you can randomly pick whatever video you have on YouTube. And we select automatically a bunch of frames. This is done using a combination of reinforcement learning and some CNN-based quality and aesthetic value estimation. You align that, we align that into a comic layout, and we turn the style into a comic one. And finally, we add bubbles with some random text or jokes. You can add it as well with your jokes, and then you can share it on Facebook. And please do, by the way, we need that. So how does it work? We have a bunch of modules that are combined together, and there's a little bit of interesting stuff happening in there, but I guess the most exciting part is that we actually were able to put everything together and make something that is fairly unique. I would say a global level, and that was all done as an output of a project with 3 students out of this university, which makes it even more amazing. So first part is keyframes extraction. We take a bunch of frames out of a video. We sample a video. We estimate the score of how representative and how actually diverse the frames are. We use temporal segmentation so that they don't overlap in time. We do some estimation of the quality, and then we do the style transfer on those frames. So let's go one by one through those modules. So first one is video sampling. What frames are we looking for? We're looking for those that are representative, so that actually represent the video correctly. So you don't want to have the video that, the frames that are just like aligned one by one or show exactly the same part of the video. You want them to actually show the story and represent the story. They also need to be diverse, which means that they cannot look exactly the same. And by exactly the same, I mean they have the same pixel values or RGB values. There also has to be some sort of a quality, assessed, or there has to be some sort of a nice visual part of those frames that we select, so that you actually see that there are not some random blurred frames that nobody wants to see. All right, so how do we do video sampling? We take a video like the one from Star Wars, which hopefully is going to load at some point. And we just take 2 frames per second. That's it, no AI. We then do summary score. So how we do a video summarization? We actually use one of the unsupervised, and now bear with me, reinforcement learning. Some of you may have heard about that. Unsupervised model for text, taking the frames that are actually telling the story. And the paper that we are based on is actually pretty interesting, because it sets up the problem as an unsupervised problem of picking the frames, a subset of frames, and this is the picking part is actually somehow similar to what robots do, and that's where reinforcement learning comes quite handy. And then they select those frames from the whole video, and they estimate the scores based on that, and this is the reward function that you're getting, and the score is based on the diversity and the representativeness of the video. So if you look at the middle part, which is the deep summarization network, it contains the CNN, which is obviously taking the images, and it converts them into a bunch of latent space vectors, and then it takes the frame by frame into LSTM and builds the probability of being picked so that the summary of a video based on a given frame is the most representative and diverse. And the actions that you can apply just by picking a frame, it's basically done with some sort of probability. And the probability is a summary score. That's how we call that. So the likelihood that somebody or agent would pick a given frame can be considered to be the score of a frame to be used in the summary. All right. So we have those summary scores, and we look at them in time. This is the temporal part of the video. So you see there, they look like stock exchange. A lot of rubbish. Nobody knows if the stock is going to go up or down. So that's a problem, because you could actually end up picking the frames with the highest value of the summary score, but they don't actually represent truly the summary or the score of the sequence of frames, just a single frame. So we add the temporal segmentation of the video. So once again, the stock exchange graph. We look at the temporal parts that are consistent from the story perspective, and we average those scores, and we only look at the maximum amount of, or maximum summary score within those temporal fragments. And so we sort them according to that. So this is our initial candidate keyframe selection result. There is a bunch of frames, still more than we need for the comics. And now we apply this static estimation. That's done using NEMA. We also have our own proprietary model for popularity prediction that we were working on for the last couple of years. And we implement here just you can think about it as some sort of a quality estimation of the frames that we used for, that we picked before. So NEMA is the neural image assessment. That's the model or the algorithm out of Google. We also have the popularity estimation algorithm that basically assesses the quality of the images. It's a very simple network, just a CNN as well, but trained on the images either from social media or Flickr or other sources with clicks and with responses of people who actually have seen those frames. Yeah, this is the NEMA model. As you see, it's super simple. It's just a baseline image classifier and fully connected layer, softmax, and the quality prediction based on the responses of people. All right, and so this is it. We have those frames, keyframes that we selected. We estimate the quality of those keyframes with NEMA, and we get a bunch of numbers. Now, to make the selection even more diverse, we look chronologically, and we pick. We use some sort of like non-maximal suppression or maximum value selection within couples, so that even if there's, this way we basically increase the granularity of our solution, and we make sure that within two of them, within the couple, we pick the maximum one. Then we move to the second couple, we pick the maximum one. It looks super heuristic, it just increases the diversity that we have at the end, because at that point, you already lost some part of the diversity that you actually measured in the first step. So it's not end-to-end. Bummer. But this is what you get at the output. All right, so you have a bunch of interesting keyframes. Now the part where you start making comics out of them, we use style transfer, and we use our own proprietary comics gun for that. So comics gun is basically, it has two loss functions, or two parts of the loss function. One of them is adversarial loss, that is focused on detecting if image generated by the network, by the generator, is a cartoon or not a cartoon. And there is a content loss that's very well known from any other style transfer method, or either from Gattes or the follow-up works. And it basically makes sure that you have the same sort of a content in both the image that you had as an input, the real image in the bottom left corner, and the one that you get out of comic, or out of comic scan. There's also a trick that people use for those sort of animations, which is blurring the edges. So we actually input a lot of data with blurred image edges, and that increases the focus of the network on the edges, because as you know, animation is a lot about edges and how people draw the lines and so on so far. So adding this augmentation with edge blurring, it's quite helpful to make the network stable and generate the results. All right, so this is the output, a sample output of the whole style transfer part. So you take the Formula 1 frame, and then you apply the different filters compared to the other state-of-the-art solutions that we tested at the gates. In the bottom, you see Cartoon GAN, and that's actually quite similar in concept to ours, but it's more trained on the anime, the Japanese cartoon version. And as you see, the colors are not that bright. They're not that colorful, and they're a bit dull. You can still test them on Comixify.ai, and you can see by yourself how different results you can get. Ours is much more bright, and especially with Formula 1 videos, it looks pretty cool. All right, so we launched the website in December, along with the paper. It got over 150,000 views within just a couple of weeks. And we generated over 35,000 unique comics right now. And why it is important that these are unique is because we actually allow people to, well, upload the videos by themselves, but also we allow them to use YouTube or TikTok or Twitter. Which means that if we already seen a video before, we were not regenerating it. We're faking that we do so that people think that we do, but we don't. All right, and there is about 15% of returning users to the website. The company got incorporated in, February, and now it's incorporated in the US. We have a trademark on Comixify. Apparently, we actually invented the phrase, which was another surprise to us. We're adding new cartoon styles, so you see here a demo of what we can do with Simpsons. There's going to be some more coming up, and we have a bunch of media coverage from Engadget through Huffington Post, MIT Technology Review, and CB Insights. All right, so now a lot of people ask now, why the hell did you come up with a company? Why would you do that? Why would you hurt this beautiful research? And we actually looked at what people are using those comics, Comixify.ai for. We, just from all the amount of data that they created, we identified a bunch of clusters of why people would use that for something that you can use in everyday life. So one of the applications and one of the reasons why people use it is to have some sort of memories summarized in a very neat way, like your wedding video. Probably not a lot of you guys are married since you're pretty young, but and since you're here and with your wives. But for those of you that have wives or husbands, it seems to be a pretty important moment in your life, so you like to memorize it and get it bright and colorful. So people tend to use the Comixify right now to create memories out of all the videos that they have. They also use that for snippets like, say, YouTubers, vloggers, bloggers, and all the other active people online. It's also quite important to see that, personally, I just look at all the politics and the videos from people talking, blah, blah, blah on videos, and it seems a bit dull. So from the data that we gathered, it seems that they're actually quite happy to add those additional context to the videos of Donald Trump which, by the way, is not that difficult to make funny, even listening to what he says most of the time. But still, you can add a little bit of a higher degree of funniness. Yeah, so we can also use that to generate some visual effects. Like here, you can obviously apply those two filters or those two guns that we train. But you can also detect humans and just cut them out of the background so that the background stays real and the humans are cartoonized, which in video editing is called rotoscopy. For a lot of applications, you use that to make animation as real as it can be. And here we can do it automatically without too much hassle. All right. All right, and yeah, last but not least, and this is the most exciting part. So I wouldn't come up with that at any point of my life, but apparently comics is very useful to treat kids with autism, and this is a call and an email that we got out of nowhere with Joanna being a teacher and a therapist with a lot of experience with kids with autism. And she said that basically she loved the tool. Can we do it a little bit more, for kids with autism? And that's an absolutely unexpected turn of events, because we were never thinking about this kind of application. And now we're actually looking at opening a separate sort of thread of development so that we can help kids with autism. And you might ask, like, how do you actually use that for therapy? I'm not a specialist, so I can just, plainly explain what she said. But it's a very good tool to train kids for social activities. And apparently kids with spectrum of autism have problem with generalization and basically finding themselves in different social situations. And that's a tool that can allow you actually to scale this and enable any one of you to create a comic with your own emotions, and then let people and let kids play with this comic and learn and train themselves for different social situations. All right, yeah, so it wouldn't be me here standing. I would probably send Adam, Maciej, or Paweł, who are the most important parts of this project. But they're actually in New York right now at BetaWorks, where we just got accepted to an 11-week accelerator, together with an investment and a lot of attention from media. BetaWorks stands behind the Giphy, Medium, Kickstarter, Bitly, all those big internet media companies, and we're right now there. And that's one of the reasons why, if you're interested in looking at comics and those sort of problems from a different perspective, just feel free to reach out. We don't have a lot of money because we're just a brand new startup, but we have a shitload of ideas on how to use comics and AI together. So if you're a fan of comics, and by any chance you know something about social media or DevOps or backend or all the other things that I just mentioned here, just feel free to reach out. And by the way, if you want to have a sticker, just come ahead, and that's it. Any questions? All right.
Let's thank Tomasz.